As you see here, we'll be studying lesson 2.1, which is about inductive reasoning. So inductive reasoning is the process of coming to a general conclusion by finding a pattern in several specific examples. We use inductive reasoning a lot throughout our day, even just the start of it. If we're in the middle of the summer and we're like, oh, we've seen it's been warm for these last several days, so it's probably going to be warm today. That's inductive reasoning. So you're coming to a general conclusion by seeing a pattern of what's happened in a lot of specific examples. Inductive reasoning, once we use it, we might come to a conclusion from that, and that is called a conjecture. So a conjecture is kind of an educated guess after you've seen several examples of something happening, so you come up with this conjecture of what possibly could happen. So it says make a conjecture describing the pattern in each series of examples, then find the next two items in each series. So this first one, it says classes beginning at 8:15, 9:05, 9:55, and as you look at that, it looks like they start every 50 minutes. So classes start every 50 minutes, and so the next one would be 10:45 and then 11:35. Here's another one, same idea. We want to sketch the next two in the series. It looks like we just keep adding another row of one more than the last row. So this row has 1, then 2, then 3. 1, 2, 3, 4. So our next row would have another row down here with 5 dots. So the 10 that are here plus 5 would be 15. And then you would have that 15 and you would add 6 to the next row, so you would have 21. So that's what those two would look like. Another one here, we have a series of squares with shapes inside it and this diagonal drawn here. So it's a circle and a triangle with a solid line, then it goes to a dashed line and then solid. So it seems like the next one will be a dashed line. Well, what's happening to the shapes here? It kind of looks like shapes are moving up to the right. So we see that this circle's down here, and now it's up here, and then it's gone. So it looks like things are going kind of out to the right. So this triangle is gone in this one, the circle moved up, and then you have the square. Then the square moves up to the top right one, and the triangle comes back in. So the next couple look like they would be this bigger square shape with a dashed diagonal. The triangle would be in the top right, and then the circle would be back in on the bottom left, and then that would happen again. And so right there we have that. The circle moves up to here, the square comes back, and then we have a solid line. Inductive reasoning is not a valid method of proof. Sometimes we see things happen a lot, so we kind of make a conjecture and we think, oh, well, this will always happen, and then something throws it off. And so inductive reasoning is not a valid method of proof. It doesn't guarantee the pattern will continue, as you see there. All you need to prove a conjecture false is to get one counterexample, and that's an instance in which the conjecture is incorrect. Now, maybe the conjecture is completely incorrect, or maybe you just have to change it to fit certain situations. So here's an example. There's several products here, 3 times a lot of things, 3 times 3, 3 times 9. And it says, Jennifer concluded that every multiple of 3 is odd. Give a counterexample to show that the conjecture is false. Well, the problem is it's always doing 3 times an odd number. So if we just did 3 times an even number, like 3 times 2, gives us 6, or 3 times 0 gives us 0. So as long as we choose an even number to multiply by, we will get that counterexample. So Jennifer's conjecture was wrong, and all we need is one example to show why, and there you have 3 times 2 is 6, which is not odd. Here's another one. Joseph claims that the function f of n equals 1/2 n cubed minus 1/2 n squared plus 2n minus 1 can be used to find the sum of the first n squares. So like 1 squared, 2 squared, 3 squared. Give a counterexample. So to give a counterexample, really what you want to do is just start plugging in values to see what they equal. And it's saying that there's a counterexample, so there probably is one. So here's several right here. So here is our formula to find the sum of the first n squares. And so what we can do here is we can put in 1. So here's 1 put in here, and it's worked out for us. You can trust the math here, and you get 1. And here's to check, well, 1 squared equals 1. It's not really a sum, it's just the first square. Then we'll get into adding here in the next one. So then you put in 2. And over here, we could actually check this first. 1 squared plus 2 squared is 1 plus 4 equals 5. Plugging in here, again, the math is done for us. We can think through it. 2 cubed is 8 times half is 4. That's where this came from. 2 squared is 4 times a half is 2, so minus 2. 2 times 2 is 4, minus 1 is 5. That one works out. Try the next one. Plugging in 3, it still works out, as you can see here. But so it looks like his conjecture, Joseph's claim, is pretty good so far. It's worked for the first 3, but then when we get to the 4th one, we see that it's actually off by 1. And so that conjecture does not hold true. So our counterexample is when n is equal to 4. So in that one, we analyzed our thinking, we looked through it, and we showed that there was some fallacies. Here, one of those ways is a hasty generalization. We saw something worked for a few examples, so we're just decided, oh, it looks like it probably will work all the time, and we make this hasty generalization. So again, mentioned before, but you can do lots and lots of examples, but it doesn't mean that it's true. Even if you can't find a counterexample right away, it doesn't necessarily mean that the conjecture is true.